Greetings, my dear students. A very warm welcome from SGT University. I am Dr. Reshu Madan from Faculty of Dental Sciences. Today, we will be discussing a chapter which confuses the best of us, mechanical properties of dental materials. As a second year student, we often don't appreciate the importance of reading material science in detail. But we have to understand that by rendering dental treatment, we aim to rehabilitate the patient both aesthetically as well as functionally. In order to achieve this in the difficult environment of the oral cavity, we need to learn the behavior of various restorative substances in the mouth. Let's start from the very basic. Stress. No, not the kind you get looking at books, but stress pertaining to materials. Solids may be stiff or flexible, hard or soft, brittle or ductile, and fragile or tough. All mechanical properties are measures of the resistance of a material to deformation, crack growth, or fracture under an applied force and induced stress. Stress and strain are two fundamental concepts that are used to describe how a body responds to external forces. When an external force is applied to a body, let's say this cylinder, an internal force equal in magnitude and opposite in direction to the applied force is set up in the body. This internal resistance to the external force is called stress. It is described as the force per cross-sectional area. This can be of three types: tensile, compressive, and shear. Tensile stress is caused by a load that tends to stretch or elongate a body. Compressive stress is the internal stress developed when a body is placed under a load that tends to compress or shorten it. Shear stress tends to resist the sliding of one portion of a body over another. It can also be produced by a twisting or torsional action. Strain is a quality that describes the deformations that occur within a body. Application of an external force to a body results in a change in dimension of that body, the magnitude of which depends on the applied force and the properties of the material. Flexural or bending stress is produced by bending stresses over the prosthesis or any other dental appliance. Difference between stresses induced in a 3-unit bridge and a 2-unit cantilever bridge is shown. Because of it being a cantilever, the prosthesis is stretching more on the occlusal surface, that is, it is becoming more convex. This is also shown by means of a simple home experiment. Notice the bending of the scale when it is supported at both ends and when it is supported only at one end. The strain may be recoverable, that is, the material will return to its original length after removal of the applied force, like in case of this elastic band. This is called elastic strain. Or the material may remain deformed, like in the case of this plastic sheet. This is called plastic strain. Each type of stress is capable of producing a corresponding deformation in the body. Therefore, stress and strain are not independent and unrelated properties, but they are closely related and may be seen as cause and effect. The relationship of stress and strain is often used to characterize the mechanical properties of materials. Stress-strain data are generally obtained using a mechanical testing machine, which enables strain to be measured as a function of stress and recorded automatically in the form of a graph called the stress-strain graph. As the stress is increased, the strain is increased. In the initial portion of the curve from O to A, the strain is linearly proportional to the stress. When a stress that is higher than the value registered at A is achieved, the strain changes are no longer linearly proportional to the stress changes. Hence, the value of the stress at A is known as the proportional limit. Proportional limit is defined, therefore, as the greatest stress that a material will sustain without deviation from the linear proportionality of stress to strain. Elastic limit is defined as the maximum stress that a material can withstand without permanent deformation. Above elastic limit, a material undergoes irreversible plastic deformation. Below elastic limit, when the stress is removed, the structure will return to its original dimensions and the material is considered to be showing elastic nature. The region of stress-strain curve before the elastic limit is called the elastic region. The application of stress greater than the elastic limit results in permanent or irreversible strain in the specimen, and the region of the stress-strain curve beyond the elastic limit is called the plastic region. Superelastic materials are an exception to this. These materials exhibit non-linear elastic behavior, and their relationship between stress and strain in the elastic region does not follow a straight line, but removal of the load results in a return to zero strain. There are several important mechanical properties measuring reversible deformation and include elastic modulus, dynamic Young's modulus, flexibility, resilience, and Poisson's ratio. When a material deforms elastically, strain for a given stress is always the same, and the two are related by Hooke's law, that is, stress is directly proportional to strain. From the Hooke's law, the modulus of elasticity is defined as the ratio of the stress to the strain in the linear or elastic portion of stress-strain curve. E is measured by the slope of stress-strain graph. It describes relative stiffness or rigidity of a material. Therefore, it follows that lesser the strain for a given stress, greater will be the stiffness and higher the Young's modulus, and vice versa. Elastic modulus of a material is constant and is unaffected by the amount of stress induced in a material. Thus, it is not a measure of strength. Material with a high elastic modulus can have either high or low strength values. For example, the metal frame of a metal ceramic bridge should have a high stiffness. If the metal flexes, the porcelain veneer on it might crack or separate. Such a material would possess a comparative high modulus of elasticity. A polyether material, on the other hand, has greater stiffness than any other elastomeric impression material. Thus, a greater force is needed to remove an impression tray from undercuts in the mouth. The modulus of elasticity is an inherent property of the material and cannot be altered appreciably by heat treatment, work hardening, or any other kind of conditioning. Dynamic Young's modulus is measured by a dynamic method. Velocity of sound wave and density of a material are used to calculate elastic modulus. Resilience indicates the amount of energy necessary to deform a material to proportional limit, or it is the amount of energy absorbed by a structure when it is stressed to proportional limit. Resilience is measured by the area under the elastic portion of stress-strain curve. Resilience has a particular importance in the evaluation of orthodontic wires. It determines the magnitude of the force that can be applied to the tooth and how far the tooth can move before the spring is no longer effective. Also, elastomeric soft liners used in complete denture treatment absorb considerable amount of force without being permanently distorted when stressed, and the energy stored is released when the material springs back to its original shape after removal of the applied stress. Flexibility is the maximum elastic or recoverable strain that occurs when a material is stressed to proportional limit. Therefore, it follows that greater the strain for a given stress in a material, greater will be its flexibility. For example, restorative materials should withstand high stresses and show minimum distortion, or should have minimum flexibility. Impression materials should have large flexibility or elastic deformation to withdraw through severe undercuts without permanent deformation. Maxillofacial materials and soft denture liners should have high flexibility. This was the end of part 1. Next time, we will cover more mechanical properties in detail. Keep learning, keep growing. See you next time.